Good afternoon, everyone. My class presentation is about 15 minutes earlier than expected. So today I would like to present our research on the title is forever economic potential for three energy conversion pathway from empty fluid branches. You can see the empty fluid branches is very rich in Malaysia and Indonesia. I'm from University. It's our Center of Sustainable Process Engineering. This is my outline. First, I am going to introduce and talk about the research objectives. And secondly, I will present in details the four level is radical economic potential, and then is the process description and modeling. Finally, I discuss some research and some conclusions. So first, is the empty fluid branches is very rich in East Asia and is one of the most recent renewable energy. It's waste of palm oil industries. So you can see the growth in Indonesia oil palm plant from 1980 to 2010 is increased very suddenly. So otherwise, there are many biorefinery processes. You can see the superstructure from one or two biomass material, and here there are many products. So this is why this process should be typical and ecologically structured. This is why we develop forever economic potential, and it includes the input and output structure, and then the process structure, and then with process structure we apply the process simulator and use a model, and here heat integration we improve the process by optimizing its network to save the energy consumption and energy consumption. Finally, the final level is economic feasibility evaluation. It supports for the decision making. Three level here is actually is same with six level of project design, and we push in one more level. Here is economic feasibility evaluation. So use this forever economic potential, we can estimate economics in early step of process development. You can see in the input output structure we can estimate how's the economic potential, and you can also propose and the concept of process design is the second step, and third step. The third step is modify the process design, and we can optimize yes here and evaluate critically and ecologically. We can also use this model for the compare many scenario and configuration, and can remove the non-economic ones. And our case study is this study in this research in three providing energy conversion pathway from 400 ton per day of gas empty fluid branches. This is first bioethanol and jet fuel production, and then is gasification and combined heat and power, and the last one is phase pyrolysis and bio-oil upgrading into hydrocarbon. Here, the first we also published one paper related to the bio-oil production from empty fluid branches, and we also published one more in gasification and combined heat power, and recently we published one in the talk about the bioethanol and jet fuel production, and also the four-level economic potentials. And I wanted this study to find the best pathway from of energy conversion from empty fluid branches, and we compare three case here, and we first we evaluate the technical evaluation. We estimate the economic potential and compare between three cases, and we also estimate the total capital investment, total production cost, and sales revenues, and compare between them. And about the criteria, we concern about the return on investment and interest of returns. Here is the four level of hierarchical economic potential. The first level, we concern about the raw material product property, production rate, plant location, and we also the process is based of continuous, and finally we has over mass balance. So this is why we can estimate the economic potential. This is the difference between the annual sales revenue and raw material cost. In the second level, we develop the process model, and this is why we can calculate the energy balance and mass balance, and use this information we can map and sizing to estimate the project equipment cost, and then the total install cost, and finally also we use this model, we also can calculate the utility cost of the plant. And the economic potential in the second level is equal first level minus the annual total install cost and the utility cost. And the third level is the heat integration based on spring technology. We recognize the heat less work, and this is why we can say the heat consumption, and we can cost some extra capital cost of the heat exchanger. And in this level, the economic potential equal EP2 plus with the energy saved by the heat integration. And the final level is the less net profit is the economic potential, and in this level we care every factor, includes the total capital investment, total production cost, tax, and we also perform the sensitivity analysis to find the key variable effect to the process. And especially in the level 4 economic flexibility, you can see the equation to estimate the total capital investment. It starts from the total project equipment cost multiplied with some factor. For example, A is installation cost factor, B is indirect cost factor, C is the project contingency factor, and D is the working capital factor. And finally, we can estimate the total capital investment. And here the total production cost is include three factors. First is raw material, and here utility cost, and CF is the fixed cost. It's include labor and maintenance, for example. And for the criteria, we can estimate the payback periods, net profit, interest of return is defined is interest rate, I. When the less profit of the last year equals 0, and we can also estimate the return on investment is the ratio of the less profit to total capital investment. In this level, we also perform the sensitivity analysis to find the key variable effect to the project criteria. Here's some assumption of and surface. Okay, it's the same initial condition. Is first of all, is wet in empty full branches. It's over 50% of water, and this approximate analysis include 38 several, 27 hemispherical, and 24 liquid. Other is ash and water. By the ultimate analysis, you can see it's 44% carbon, 6% hydrogen, and 43% oxygen, and other nitrogen and ash. And the plant capacity, as I said, is 400 per day of gas ESP per day. And dry ESP empty properties have low heat value about 18 megajoule per kilowatt. Here is the economic assumption for example, plant operability is 8,000 hours per year, and starting up to 6 months, and project life 20 years. The income tax in Korea is 22%, and energy cost, fuel cost, and the water cost. I'm moving to the project description and modeling. You can see this is the bioethanol and ZSP production, include HR 9 area, and it is a feed 4,400 tons per day, and the product is main product is ethanol about 80 tons per day, and jet fuel about 22 tons per day. And its input line area, you can see from 100 to 800. This includes feed handling, pre-treatment, fermentation, purification, and with treatment, utility, and boiler steam turbine, and jet fuel production. The bioethanol production, we use two-step pre-treatment, first acid and second alkali. By the use of acid pre-treatment, we can extract the cyanide from the biomass and use for the jet fuel production. And in the fermentation, we use separate hydrolysis and some fermentation methods. It's a jet fuel is from cyanide and by 4 steps: dehydration, condensation, hydrogenation, and hydrodeoxygenation. And this no waste is this conceptual process design with is recycle, treated and recycle, and the solid waste is going to generate electricity as well as steam. And this plan applies the heat integration is in level 3. So this is why we can say significant raise utility cost. And process design, this design based on the pilot plan developed by Sandok company in group of 4 area from 100 to 400. So we advance the process design to full plan, and this is why the low waste, and we propose jet fuel production to increase the benefits of the process. And secondly is the gas efficient combined heat and power. It's the same fixed capacity, and the product is electricity about 12 megawatts, and as a byproduct is a high pressure steam 64 tons per day, and the medium pressure steam is about 170 tons per day. And the conceptual process design includes a 6 area. For the electricity generation, we use a circulating fluoride bed to generate syngas, and then use a gas engine and steam turbine to generate electricity. And also this create no waste with the electricity. And but this case cannot apply the heat integration because the heat consumption is this gas efficient plant. And this also developed based on the pilot plant. This is contrast by the unsoil synthetic. And the case 3, the test process and bio oil upgrading. You can see the same feedstock, and the product is gasoline, light gas, and diesel, and byproduct is electricity and steam, medium steam. And the conceptual design is in 8 area, and it's a hydrocarbon based on the fat resid in area 200, and the bio oil upgrading in area 800 for the upgrading into hydrocarbon. And this blend also low waste with the Egyptian char and incondensable gas is burned and generate electricity and steam. This case can apply the heat integration to save utility cost. And it also developed based on the pilot plan contracted by Daekyung Esco company. And this is the result. The first is equilibrium potential. We compare during forever. You can see the equilibrium potential is more reliable to the 4 step forever. And you can see the K3 start is equilibrium potential is smaller than K1 and 2, but from the level 2 is higher. And then we compare the equilibrium energy conversion efficiency, and the first efficiency is defined by percentage of low heating value of the product to raw material, and you see the total input energy K1 is about 58 megawatt, K2 and 3 about 41 is from DSP, and the the output is about 21 megawatts and for O3 case. And this was energy conversion efficiency is smaller is K1 and K2 and 3 is about 52%. But you can see in K2 and 3, 42% is contributed by the thermal heat, steam and hot water, and 21 in K3 contributed by the steam and hot water. So even it's smaller, but it's more valuable. This is why you can see the annual sales revenue is the biggest. And result is total capital investment and total production cost. You can see the 3K is just less than half of K1 and K2. So total capital investment in K2 is very small. K1 is biggest. Compared to the total production cost, the K2 is smallest. Is about 1/3 of K1, and K3 is the small, higher than K2. K2 and 3 is utility cost is 0 because electricity and steam is byproduct in K2 and 3. K1 we still have to apply to supply the electricity and steam. Now we compare the criteria for 3K. You can see the K3 is most economic feasibility because it's a high return investment, lower payback periods, and also higher internal rate of return. And if we consider the return on investment about 10%, K2 and 3 it can be economic feasible. And K1 is hard to get a good feasible because very high total capital investment and utility cost. And this we perform the sensitivity analysis, and you can see the K1 need to double the size to have a return on investment about 10%. K2 3 is about even it's a half the play case, and it's a sensitivity analysis. You can see the capital investment and ratio is strong compared to the economic criteria, and the return on investment and the interest return of K1 all the way higher than K2, and K2 all the way higher than K3. And as we conclude our research, first we develop forever economic potential, and we estimate the economic criteria, and we study the effect of plant capacity and also sensitivity analysis, and we found that the hydrocarbon production from biogas pyrolysis and bioupgrading is more economical feasible, and this method can apply for other projects, especially for new and promising energy conversion technology. This is supported by the research evaluation. And thank you for